Alright, hello YouTube. Today I'm coming at you live with probably the most important math discovery of the last 100 years, probably, made by me. The, a constant to rival the importance of E, pi, 1, all your favorites. This is going to be your new favorite. This is the glass constant. So what it is the difference between this function here e to the minus x squared, or the Gaussian function, and this function right here, hyperbolic secant. Both of these are convergent, so the area I'm shading in purple here eventually converges to a number, and that number is the glass constant. And the glass constant comes out to be something like 1.369, I think, or just goes on. But the real important part is how we calculate the glass constant. So in order to find the glass constant here, we're we're gonna have to take two integrals. Kind of weird ones. Secant x, the hyperbolic secant of x from negative infinity to infinity, and the ever beloved Gaussian integral. So this we'll call I2, this we'll call I1. We're trying to solve for. Come back at the end, I promise. So this, as we know, it's a difference of areas. The glass constant here will be the difference between I1 and I2. So now we actually have to solve for these, and we'll start with hyperbolic secant. Alright, to solve this integral, let's first just rewrite it. So hyperbolic secant is 1 over hyperbolic cosine. So that just comes out to be 2 over e to the x plus e to the minus x. And now that we have it written like this, I see right away we could manipulate this a little bit. So we're going to multiply this by e to the x over e to the x, which, as you know, is just 1. It doesn't change anything. Which, that'll now come out to e, there 2 times e to the x over e to the 2x plus 1. And what you could, the more discerning viewers of our audience could see here is that we have a very nice setup for a certain inverse trig function. Because e to the 2x squared is equal to just e to the x squared. And 1 is 1 squared. So let's set up our substitution. We'll set e to x to be equal to u, and this one always works out easy. Du is equal to e to the x dx. We'll sub that in, and now we have 2 du, or that could go anywhere, it's du, for u squared plus 1. And this integral looks a lot like arctangent. Well, it is arctangent. This integrates into arctangent. We'll take the constant multiple, move it out of the integral here, and just say this is 2 arctangent of u. We'll sub u back in. This is 2 arctangent of e to the x. So this is our final answer. Now we have to plug the bounds in. Improper bounds like this with infinity and negative infinity are kind of weird. So we're just going to rewrite these as 2 limits. We'll start with infinity, I guess, the top one. So we'd say the limit as x approaches infinity of 2 arctangent of e to the x. So we know, you probably do know that as e to the x approaches, as x approaches infinity of e to the x, it approaches infinity. So we could basically just say, like, this arctangent of infinity. But if you think about what arctangent is, and look at that graph here, arctangent kind of has a asymptote at pi over 2. So as arctangent of x, as x approaches infinity, we could say that this is approaching pi over 2 times 2, approaching pi. Now for the limit as x approaches negative infinity, well, we know that e to the negative infinity, this is 0. So we could just say 2 times arctangent of 0. And we know that we'll draw arctangent again. Well, arctangent at 0 is at the origin here, so this is 0. So now we do what we do with integrals, minus subtract the bottom bound from the top bound. And we could say from before that I1 comes out to be pi. So remember that. Now we're going to solve for I2. And this integral is weird because it is non-elementary. We can't just solve it through our normal integral solving means. We're going to have to get a little weird with this one. We're going to need to use some Calc 3 exciting things. So what I'm going to say is set this equal to I2. And I'm going to square both sides. Right? I could do that if I want. So now we say that e to x minus x squared integral there equal to I2 squared. So I'm just going to write out another integral like this. But this time I'm going to use y as my variable. So same thing here, you know, I didn't really change anything about the integral, I just introduced a new variable. Now we're going to multiply these two together and get a little bit of a double integral going on here. And I'll go ahead and write that out. So now we have this double integral here, and we all know how exponents work, you know. If I have e to the n times e to the m, I could just add the exponents together. Same goes here. So I'm going to do that. And what you could see here is now we have a perfect setup to convert this to a much more workable use of my favorite thing ever, polar coordinates. So we're going to convert this to polar coordinates and then we'll be able to solve it because polar coordinates rock. Right, now that we have our integral here in polar coordinates, we redefined our limits because the changing of coordinate systems kind of changed some things around. And we threw in our little determinant here. Now this is just a solvable integral, right? So let's just set up our u substitution. We'll let u be r squared du minus 2r squared, not r squared. And what is important that we got to remember to do is redefine our limits of integration. So we could just see right here, we'll just take the limit as u approaches infinity, which would be negative infinity, you know, it just got the negative sign out front. And we will take the limit as u approaches 0, which plug in 0 here, that's just 0. So when we're rewriting this integral, we'll have our new bounds. Now we could just set up the substitution. Pretty easy, you've done this before. Now we have this, like, nothing integral set up, so we'll just integrate it. I need more room here, so I'll make that happen. Alright, now we just gotta evaluate this integral. So e to minus infinity is 0. E to the 0 is 1. 0 plus 1/2, that's 1/2. Now, we just got 1/2 here. And we could just sort of, this is just a constant multiple. So we could just sort of slot these two bounds in. 1/2 times 0 is 0. 1/2 times pi is pi. And now we know that pi is equal to I2 squared. So if we take the square root of both sides, we got our answer. This is I2. Now we got I1 minus I2, pi minus the square root of pi. And this comes out to be like 1.369, I said earlier. This is a class constant. We found it. Alright, thank you all for watching this video about my revolutionary discovery. If all your problems disappear in a matter of months, weeks even, you'll know who to thank. Now we can start inventing pretty much anything we want now that we know this. So, if you've seen this video, you're one of the first people to be let in on one of the most important discoveries ever. So you should feel pretty good. Alright, good night. Divergence and curl coming soon.